Hey ChemStars, here's your Chapter 9 video homework solutions for Honors Chemistry, pages 16, 17, and 18. We're looking at some BCA tables with limiting reactants. So let's get started on number 1. So question number 1, it says, if you have 16.7 grams of calcium hydroxide and 32.9 grams of hydrochloric acid, what is the limiting reactant? And how many moles of the products can be made? So first things first, you've got to write and balance your equation. Then let's say what we know. We know that before the reaction starts, there are no products. We're going to be creating some positive amount of products, and I've started writing the mole ratio here. And at the end, there'll be something made, and one of these will be limiting. It'll go to 0, and one of the reactants will be left over. It'll be excess. So we have to actually figure out how many moles we're starting with. So to do that, we've got to convert grams to moles using the periodic table. Let's look at calcium hydroxide. So CaOH, let's find our periodic table. So calcium hydroxide, CaOH2. Oh, look at my handy dandy periodic table of science. It's written right there. Calcium's molar mass plus oxygen plus hydrogen hydroxide, 2 of those, 74.10 grams per mole. So we're going to put that into our factor labeling problem. 74.10 grams per mole. And look at this. You can get a free TI 84 calculator, a 6-month subscription. I posted the link on Google Classroom for you. So let's clear, how do I clear all my history? Well, there we go. 16.7 divide by 74.10. Oops, oh boy, 74.10. There we go. And we should get 0.2253. 0.2253. Now they gave me 3 sig figs in the problem, so I'm just truncating after 4 sig figs right there. Let's plug that into the problem, 0.2253. Now we got to figure out our moles of HCl. So go back to your periodic table. HCl, hydrogen plus chlorine, 36.45 grams per mole. So 36.45 grams per mole. So we're going to do 32.9 grams of HCl, divide by the molar mass, which is 36.45. And that's going to be 0.9026. 0.9026, and that's how many moles of HCl we have. Okay, so right now we don't know which one's limiting and excess, but let's just take a look at it. Okay, let's just assume the first one's going to be limiting. If that's true, we're going to use all of it up and there'll be none left over. Look at your mole ratios up here. We need twice as much HCl as calcium hydroxide. So if we have 0.2253, how much of the HCl would we need? We would need double that, so 0.44 or 0.45. Do I have at least 0.45 of it? Yes. So when I do that little self-check, that can help me pick the right limiting reactant. If you pick wrong, that's okay. You'll get a negative number here. Then you just have to erase it and go back and redo it. For the sake of showing you that mistake, let's do it the wrong way first so you can see how to fix your mistake. So let's say, oh, this one's limiting reactant, because I think it is. We're going to use up all 0.9026 and there'll be none left over. Well, then how much calcium hydroxide will I have to use up? I'll have to use up 0.9026 times the ratio, which is 1/2. So divide that by 2, I'm using up 0.4513. So this number right here is actually 0.4513. So with this term right here, we started with 0.2253, and we're using up 0.4513. How much is left over? Negative 0.226. So when you see that, not possible. That means we chose the wrong limiting reactant. If you ever do that, don't panic. That just means we got to erase it and go back and pick the right limiting reactant. So let's get rid of that. That was wrong. Okay, so now we're saying, aha, this one's the limiting reactant right here. And so it should go to 0. This one should be excess left over, and let's try those numbers now. So 0.2253, using all of it up. And then how much HCl? We're going to use 0.2253 times the mole ratio, which is 2/1. So 0.2253 times 2, so 0.4506. So I'm using up right here. Oops. I'm using up 0.4506. So if I start with 0.9026 and I use up 0.4506, how much is left over? 0.452. So there are going to be 0.452 moles of excess hydrochloric acid left over. So now I know that this works out. I have one thing gone to 0, that's my limiting reactant, and I have some excess moles of the HCl left over. But I still haven't answered the question. They want to know how many moles of each product can be made. Okay, so this is my limiting. This is the ingredient that I'm running out of. So we're going to put that coefficient in front here to figure out how much of each product is made during the change. So now here it's 1 to 1, and over here it's 2 to 1, so 0.2253. So if we started with none, and we created 0.2253 times 1, how much is there at the end? 0.2253 moles. Now, this is where we want to round for our sig figs. So that's going to be 0.225 moles of CaCl2. And then over here, for H2O, for our water, we've got the same thing. But now it's times 2. So 0.2253 times 2 divided by 1, 0.4506. So 0.4506. And that's going to be my moles of that. But remember, 3 sig figs, 1, 2, 3. This will round to 0.451 moles of my water. So that's how you do a limiting reactant problem, when they only give you grams of each of the reactants. Remember, if you get a negative answer, it just means you chose poorly. You must go back and try again. The only added layer of complexity on this is that they might not want moles for the final answer. They might want grams or volume of a gas, and you already know how to do that. Okay, let's look at number 2 on page 16. And remember, if you have any questions, make sure you email your teacher for help. If you have 2.23 grams of aluminum and 0.02 moles of copper 2 sulfate, what is limiting reactant? How many grams of copper can be made? So we're adding that extra layer of complexity here. They gave us grams, they want grams out. Let's set up what we know before we start working through some of these problems. So we have aluminum plus copper 2 sulfate. Remember that copper 2 is Cu2+. Sulfate you've memorized, or you can look it up on your polyatomic ion list. It's SO4 2-, crisscross, CuSO4. This is a single replacement with aluminum replacing the copper, and then we're going to have aluminum sulfate. Aluminum's a 3+, sulfate's a 2-. So here is where we're going to pull all of our mole ratios from. It's our balanced chemical equation. Look at your coefficients there. And now let's go back to the problem. Okay, grams of aluminum. We've got to take the grams of aluminum, divide it by aluminum's molar mass, which I check right here on the periodic table. It's 26.98. So take that, divide by that, you get 0.0826 moles of aluminum. So before the reaction starts, here's how many moles of aluminum I have. They were nice, they gave us moles of copper, and we know that before the reaction starts, there are no products. So look at these two numbers. Which one do you think we'll run out of first? If you look at just at the ratio here, we need more copper than we need aluminum. Do I have more copper than aluminum? No, so a good guess would be, let's pick copper sulfate as my limiting reactant and go from there. So I'm going to use up all 0.02 moles of it, and there'll be none left over. I'll know if I chose correctly once I figure out aluminum's number. So I'm going to be using up 0.02 times the ratio of aluminum to copper. I'm just going to kind of put this in brackets here. We've got to figure out what that number is. Let's clear everything. Oops. Clear. So we're going to take 0.02 times 2, divide by 3, and that's 0.013 repeating. So this is actually 0.01333. That's good enough. Okay. So we need to take 0.08265 minus the 0.01333. And how much will be left over? 0.06932. So at the end, there'll be 0.06932, and that's going to be moles of excess reactant left over. That means we chose correctly. So this was my limiting reactant. I'm going to use all of it up, and it's determining what I can use for everything else. Remember, if this came out negative, it means we chose poorly. Erase it, go back and pick the other one. Okay, so how much copper can be produced? They want to know how many grams of copper. So I'm going to be creating 0.02 times the ratio of copper to copper sulfate, which is 3 to 3. So 3 to 3, it's 1. So I'm producing 0.02 moles of copper. So we need to take that moles out of the BCA table. Remember, BCA table, only moles go in and only moles come out. So 0.02, and then we need to multiply by the molar mass. So check your periodic table. Copper is right here, 63.55 grams per mole. So we're going to take 63.55 times 0.02, and we're going to get 1.271. 1.271 grams of that solid copper made. Now let's check for sig figs. Right here there's 3 sig figs, but did you notice this number only has 1 sig fig? That means I can only technically go to 1 sig fig here. So how much copper did I make? 1 gram of copper. Hopefully when you're in chem lab, you'll be more precise than just 1 sig fig. Okay, that's the end of our page 16. Let's go to page 17. Okay, so here's another problem. We've got a combustion problem where we've got 25.7 grams of octane, and I came over here and I already converted that to moles for you. If you want to check the periodic table, octane, that prefix oct, that tells you there's 8 carbon, and there's how I got the molar mass for octane. So here's my moles of octane with 12.7 liters of oxygen gas. So over here, I divided by my constant. At STP, 1 mole of gas is 22.4. Here's my moles of oxygen. So before the reaction starts, here's what I have. So what do you think we'll run out of first? We need about 12.5 times as much oxygen as the hydrocarbon. Look at my numbers. Do I have 12.5 times as much oxygen? Could this be limiting? Doesn't look like it. So let's go through and assume that we're going to run out of oxygen first. That's not usually typical. Usually there's just oxygen in the atmosphere, but this one they're saying we're in a controlled environment where there's only 12.7 liters of oxygen gas. So we're going to say that this is limiting. So 0.5669, we're going to use it all up. There'll be none left over. So how much of the octane am I going to use up? We need this to be a positive number left over at the end if we chose correct. So we're going to use up 0.05669 times the ratio, oops, wrong way, 0.5669 times the ratio of the unknown octane to the known oxygen, okay? And we want to get what this number is. So we have 0.5669 divided by 12.5. 0.04535. This is 0.04535. Okay, now looking at that first off, are we going to get a positive number? Yeah, we will. Okay, so take 0.2249, that's my moles of original octane I had before the reaction, and I'm using up 0.04535 approximately. I'm going to have 0.1795 left over. 0.1795. And that's going to be my moles of excess reactant. Okay, so now we know that this right here, this was indeed limiting. It ran out. And so we're going to use that number to figure out everything else. They want to know liters of water vapor and grams of CO2. So I've got to do both of these problems right here. Okay, so we've got 0.5669 times the ratio of carbon dioxide to oxygen. Okay, and let's figure that one out. So 0.5669 times, what are we at here, 8. And then we've got to divide by 12.5, and that's going to give us 0.3628. 0.3628, that's supposed to be an 8, and that's going to be moles. Let's do the conversion right here. So we want to get rid of 1 mole, And for carbon dioxide, they want grams. So carbon dioxide, CO2, 16 plus 16 is 32, plus carbon, 44.01. So this one is 44.01 grams per mole. So how many grams of CO2 will we have? Times 44.01. We're going to get 15.967 grams of CO2. So 15.967, that's going to be grams of CO2. But let's look at our sig figs. We want 3 sig figs. Okay, that makes it tricky, doesn't it? That rounds it up. So this is going to be 16.0 grams of CO2 at the end. Good. Sorry, we had to kind of squeeze that in there, but let's look at water. This time they want to know liters of water vapor. Remember, this is going to be really hot. We should have a delta over the triangle. It's a combustion reaction. It's going to be carbon dioxide gas plus water vapor as a gas because it's so hot. So how much water vapor am I making? I'm making up that coefficient from the limiting reactant, so 0.5669, times the ratio of the unknown water vapor, which is 9 over 12.5. Okay, I'm going to try and kind of block this out over here. So on our calculators, we've got 0.5669 times 9, and then divide that by 12.5. 0.4081. And that's going to be my moles of water vapor, but they don't want moles, they want a final answer in liters. So 22.4 is that conversion factor. Okay, so take our number there times 22.4, and we get 9.142. 9.142. And we want 3 sig figs, so 1, 2, 3. This is going to be 9.14 liters of the water vapor. Good. That's probably the trickiest problem you'll see in this whole unit, because you were given grams of both, you had to figure out limiting, and then they didn't want moles of the products, they wanted grams and volume. So this shows all the skills that we built up all year. Stoichiometry, mole conversions, predicting products, balancing chemical equations, it's all there. Okay, I've got 2 more on this page. Let's go through these. Here, this might be helpful. I should put the screen up here, the shade. How about gold today? Why not? Okay, number 4. Okay, number 4. 3.4 times 10 to the 22nd atoms of iron. They're being sneaky here. That means we've got to come over here, convert atoms to moles, dividing by Avogadro's number. So here's my moles of iron I'm starting with. React with 18.7 liters of oxygen. They're being sneaky again. So we've got to come over to the side, convert our liters to moles, and plug in our moles. Remember, only moles go into the BCA table. Before the reaction starts, we don't have any rust. So this is a synthesis reaction. This is what happens to any untreated iron left outside. It will form iron oxide, that orange rust you might see around your car wheels. And before the reaction starts, there is no rust. Let's look and try and think intelligently about what we'll run out of first. We need more iron than oxygen, if you look at that ratio. Do I have more iron than oxygen? No. I have a lot less, so I'm going to use up all this tiny amount, and I'm going to have some excess oxygen left over. So we're going to use up all 0.05, none left over. I'm starting with 0.8348, and I'm going to use up this number. So let's check on our calculator. Let's see how much I'm actually using up. So 0.05645 times 3 divided by 4. I'm using up 0.0423. So this number right here is 0.0423. So without even doing the math, look at it. 0.8 minus 0.04. Will there be excess left over? Yes, there will be for sure. Okay, so we can go ahead and say that iron is for sure limiting. And they want to know how many grams of iron 3 oxide, how many grams of rust are produced. So I'm going to be producing 0.05645 times 2 over 4, which is really, we're dividing by 2 there. So 0.05645 times 2 divided by 4 for the mole ratio. I'm getting 0.028225. 0.028225 moles of iron 3 oxide. And then we've got to multiply it by the molar mass. So go to your handy dandy periodic table. Oh, look at that. Iron 3 oxide right there. 159.70 grams per mole. So take back our calculator, times 159.7, we'll get 4.507 grams. 4.507 grams of iron 3 oxide. Last step, round for your sig figs. Well, here there's 3 sig figs, but here there's only 2. So I'm going to be limited by those 2 sig figs. So 1, 2. This means I'm going to produce 4.5 grams of our iron 3 oxide, Fe2O3. There we go, Fe2O3. That's our final answer. Okay, one more problem on page 17. I'm proud of you guys for sticking with it and working through all these problems. Let's say for number 5, if 433.07 grams of barium acetate reacts with 122.6 grams of sodium sulfate, how many grams of precipitate are formed? Okay, so this one, we're kind of going back to some of our Chapter 8 predicting products. We've got to figure out if the reaction works and which one's aqueous and which one's solid. So here is my equation. Barium's a 2+, so here's barium acetate plus sodium sulfate gives me barium sulfate. Go and look it up on your solubility chart. You'll see that it's a solid, and then sodium acetate is aqueous. Okay, so we need to figure out the molar mass. Then we've got to put in our moles, figure out which one's limiting, and figure out how many grams of barium sulfate. So let's go to our periodic table. Oh boy, I don't think we have those molar masses here, but that's okay. We can figure it out pretty easily. So let me clear out a lot of this. Okay, so we need to do some molar mass work here. So on this one we have BaC2H3O2 2. Oh boy. Okay. BaC2H3O2 2. So what is that going to be? So here's barium, 137.33 plus 2 times carbon, which is 12.01, plus 3 times hydrogen, which is 1.01, plus 2 times oxygen, which is 16.00. Whew, okay, we can do it. We have the technology. So let's clear everything out here. Okay, so we need to take 16 times 2 plus 3.03, that's my hydrogen number, plus 2 times carbon, so plus 24.02. Oops, 24.02. So that's the mass of just the acetate, but there's 2 of them, times 2, plus we need to add the mass of barium, which is 137.33. So the molar mass of barium acetate, 255.43. This will be equal to 255.43 grams per mole. Okay, so where are we at right here? .43. So how many moles of barium acetate do I have? We've got to take our 433.07 grams that were given in the problem and divide by the molar mass we just solved for. Divide by 255.43, and that's going to give us 1.695. Oops, ooh, too big. There we go. 1.695, and that's going to be how many moles of the barium acetate we're starting with. Okay, now we've got to do that same thing to figure out the molar mass of sodium sulfate. So Na2SO4. So go back to your periodic table. We've got Na2SO4. So we have sodium. So there are 2 times the molar mass of sodium, which is 22.99, plus 1 times the molar mass of sulfur, which is 32.07, plus 4 times the mass of oxygen, which is 16.00. So let's clear this out. We have 4 times 16, which is 64, plus our 32.07 for sulfur, plus 2 times 22.99 for the 2 sodium, 142.05. 142.05 grams per mole for our sodium sulfate. Okay, so if we have 122.6 grams of sodium sulfate given in the problem, and we need to divide by 142.05 grams per mole, that means we have 0.863. 0.863, and that's going to be how many moles of sodium sulfate I have, 0.863. Now this is nice right here because look at the ratio, 1 to 1. I need the same number of moles of each one. So which one of these is less? The sodium. So I'm going to use up exactly all of that sodium sulfate. There'll be none left over. Just be a 3 there. This is my limiting reactant. That means over here, as my double check, this should be excess left over. So how much of this am I using up? I'm using up 0.863 times the ratio, which is just 1 to 1 here. So if we have 1.695 minus 0.86307, let's give some more sig figs there. We're going to have 0.8319 left over. We're going to have 0.8319 left over, and that is excess, okay? So that means I've done it right, picked the right thing. They want how many grams of precipitate are made. Well, this one is a solid, this one's aqueous, so we just need to focus on our barium sulfate here. So our coefficient is 0.863, that's supposed to be an 8. The ratio is 1 to 1, so how many moles did I just make? 0.863. Now I've just got to multiply by the molar mass of barium sulfate. So BaSO4. Go back to your periodic table. We need to find BaSO4's molar mass. So here's my barium, here's my sulfur, here's my oxygen. So it's going to be 1 times 137.33 plus 1 times sulfur, which is 32.07, plus 4 times oxygen, which is 16.00. Okay, now we've got to add those up and put it back into my problem. So 4 times 16 plus 32.07, that's the sulfur, plus the barium, 137.33, and that gives us a mass of 233.40. 233.40 grams per mole. 233.40. Okay, so now all we have to do is take that times our 0.86307 number, that's my moles, and we get 201.440. So 201.440, and that's my grams of solid product. But never forget sig figs. 1, 2, 3, 4, 5. 1, 2, 3, 4. I've got to go to 4 sig figs. 1, 2, 3, 4. This is going to be 201.4 grams of the solid precipitate, which is barium sulfate. Okay, we've got 1 page left in this homework assignment. Okay, I know it's going to be a long video, but there's only 2 problems left on this page. So page 18. Neuroscientists believe that the only chemical in chocolate that may have the feel-good effect on the human brain is phenylethylamine, PEA. Although PEA in chocolate occurs naturally, it can also be made in the laboratory by the following reaction. Okay, so I want you to just check what I have so far. Make sure you go and set up everything, convert your grams to moles, pause the video, then come back and check in with me, okay? And I also have a setup here you can check real quick too. Okay, so pause the video, come back, and check our page 18 together, please. Okay, let's check your work and see how you did. So ammonium formate, molar mass should be 63.06. How do I know that? Well, Google told me, and I rounded to our correct number of sig figs from our periodic table, which would be right there. Okay, so, and then also, what's the molar mass of the acetophenone? Well, Google can tell you that one too, but do use your periodic table. So here's my moles of the ammonium formate. Here's my moles of the acetophenone. Which one's going to run out? They're in a ratio of 1 to 1. This equation was already balanced, so this will be limiting. We'll use it all up. All of this many moles of excess. And then they really want to know about the PEA. They didn't ask anything about the CO2 or H2O. So PEA, I'm creating 1.04 times the ratio, which is 1.0, which is 1 to 1. So this is how many moles I've made of PEA. That's all the BCA table stuff. Now let's look at the analysis questions. Okay, they want to know how much can be made from 75 grams. Okay, we did that. We got the moles. They didn't ask for what unit, but we know there's going to be 1.04 moles. Let's go ahead and convert to grams. So PEA, what's the molar mass of PEA? 121.18. So take that times the molar mass. You should get 126.027. Don't round this number yet. We do need to go to 3 sig figs on everything. 1.04 is already at 3 sig figs. If we did go to 3 sig figs, it would just be 126 grams. But I'm telling you not to round yet because the next couple questions, we're going to need to use that number again. Okay, what's the mass of the excess? So we have 0.149 left over times its molar mass. Round to 3 sig figs. We have 9.4 grams of excess. So we started with 75 grams of the ammonium formate, and there's 9.4 left over. Now here's our last question. If we actually made 100 grams, what's the percent yield? I know it says theoretical, but it should just be percent yield. The theoretical yield is right here, what we got from the BCA table. So percent yield is actual over theoretical times 100. The actual is what's actually made in the lab. The theoretical is from the BCA table. So my equation here is 100 grams actually made divided by the theoretical 126.027 grams from the BCA table times 100. We get 79.3% yield. Okay, one last problem. So it says 15.5 grams of sodium hydroxide reacts with 46.7 grams of sulfuric acid. Here's my chemical equation. And then we've got to convert all of those grams into moles. I've already done that for us right here. I did it down here on the bottom. So we have to take sodium hydroxide. Its molar mass is 40 grams per mole. So that's how I get my 0.3875 moles. Sulfuric acid, H2SO4, its molar mass is 98.09, so I have 0.4765 moles. Take a look at those. Which one am I going to run out of first? I need twice as much sodium hydroxide. I'm going to end up using all this up. If I picked H2SO4, I would have needed 0.8 something moles of sodium, which I don't have. This is my limiting. It all gets used up. How much of the sulfuric acid gets used up? Well, that coefficient times the mole ratio. This is my excess left over. So how many moles of excess? We've got 0.283 moles of the excess H2SO4. Well, how many grams? What do? I take that 0.28275 number, don't round it, multiply it by the molar mass of sulfuric acid, and that's going to be 27.7 grams of excess left over. Okay. Last question is, how many grams of sodium sulfate are produced? So we start with none, and we're creating that number from over here from the limiting reactant times the mole ratio, which is 1 to 2. So we're creating 0.19375 moles. They want grams. So take the moles and multiply it by the molar mass. Molar mass of sodium sulfate from previous problems is 142.05. Multiply those together, you get 27.52, but then round for your sig figs, you get 27.5 grams. That's it. We did it. We're done with page 18. Great work today, Chem Stars. Email your teacher if you have any questions. See you next time. Bye.